Oh, good, it's working. I haven't even posted the announcement yet. There you go, announcement's posted. We will get started in about 10 minutes. Yeah, I figure some people are just bouncing around on YouTube already most of the way there, and then you see the thing, like, oh, Wes is up. Guess we're working. I have to move things around here. Let's see here. Yeah, I hear you there. I have a 2-hour break between lectures, so I did some setup and then basically took a nap with the cats. Which wasn't really much of a nap because that's how cats work. Anyway, I'll be right back. Hi, everybody. We're going to get started here in just a second. Give people a chance to filter on in. We will be working on Chapter 2 materials today, so if you have the slides for that handy, you're all set. If not, take a quick second to go grab them. Have some paper handy and a calculator, because you're going to need it today. All right. Let me just do something on my end here. Okay. So, I didn't hit this button. There we go. That's what I wanted. All right. Hi, everybody. Welcome back to Chem 121. This is the Thursday lecture. We did Chapter 1 on Tuesday. We're going to continue with Chapter 2. Chapter 2 is one of the math-heavy chapters in this class. Generally speaking, the way that math works in Chem 121 is that we hit on it in this chapter, Chapter 2. We're going to spend quite a bit of time here. Then we will come back to it when we get to Chapter 6. And then it will be peppered in throughout the rest of the quarter. So 2 and 6 are the big math chapters. So you can mentally prepare yourself. I know a lot of people have math phobias. Not big fans of math. If that is the case, fair warning, we are going to do a lot of it, but you will have a lot of practice. I'm going to type something in the chat. I see somebody is typing in there. Everybody can hear and see me and see the stream, right? Earlier on, we had issues with it. So if there is something wrong, let me know. If there's nothing wrong, also let me know. All right, there's my stream of yeses coming in. Okay, cool. YouTube was trying to make me do something differently to stream because it's apparently updating a feature or whatever, and so in order for me to not have to keep clicking on that, I was like, oh, I'll try it out today. Well, there's an extra button I had to press, and I didn't press that, and my students were like, is there supposed to be a stream? It's been 5 minutes, and it's just showing a blank screen, and I was like, oh, crap. Okay, so cool. If everything's ready, then without further ado, we'll keep going. So today we're going to talk about a bunch of units. Units are things that you measure things in, like feet or inches or centimeters or whatever. Some of those units are going to be common for science. Some of them are going to be common for America. Unfortunately, science and America are mutually exclusive, it turns out. Let's explore some of those relationships in more detail. So the first thing we want to do is we want to define what a measurement is. So a measurement is a quantity that represents how much of something you have in some dimension. So here are some examples of measurements here. Like if I wanted to weigh out some medicine, and maybe the medicine was a blue powder, but I only want to administer a certain amount of medication to a patient because too much would be toxic and too little would be ineffective, I need to be able to make a specific amount available. Maybe I need to know, like, which correct gauge needle to use for drawing blood or something. Or maybe I just need to know how much I need to put in an IV bag so that I can administer the correct dosage. Or how quickly it needs to be administered, or something like that. Whenever we take a quantity of something, we're going to call that a measurement. Now, measurements have 2 parts to them. And those are the following. So the first part of a measurement is the value. That's really terrible. Hold on. Let's try that again. I just got to move my pad farther up so that I'm not writing on the edge of my desk here. There you go. So now I have somewhere to put my hand, and my handwriting will actually look reasonable. All right. The value is just a number. And then right here, which is hard to see actually, if you look in that circle that I drew, it says 0.01 grams. That grams represents the units. Oops, I accidentally hit my button on my pen. That grams represents the units of the measurement. So all measurements have both a value and a unit in order for them to be a measurement. The last thing that's important about a measurement is that you have to use some sort of tool to make the measurement. Measurements can't be made by people. If we do something like count the number of things, that's not actually a measurement because you are getting an exact number of things with no error involved. Measurements will always be used or will always be made with tools such as a ruler or maybe a device such as a temperature sensor or a balance or a piece of glassware or something like that. And we're going to explore some of those tools later. Now, when you make a measurement, it's very important that you have the units associated with it. For example, this sign right here, you'll notice that there aren't any units in this blank here. 65 what, officer? I was going 65 meters per second. Don't actually try that. That won't hold up in court. But to a scientist or anybody in the healthcare profession, seeing this sign and interpreting it literally is not only meaningless, it could be dangerous. What's important here is that we got to actually have the units associated with this in order for it to be a measurement that we can interpret and then use. So again, we got to have a value. That's going to be this 65 right here. And then we got to have a unit, and that's going to be the miles per hour here. When you report numbers to me in either like a quiz or an exam or some sort of worksheet or whatever, if you report only the number, the answer gets marked incorrect. It's very important that you interpret your measurements with both parts of this. The number seems to be the important part, but the unit is what conveys the information to the person that you're giving this number to. Consider if you are doing a calculation and then you had to give your number to a person, and then that person takes that number and gives it to another person, who then gives it to another person. You want to make sure that that information gets all the way through the chain of command in its entirety. And the only way to do that is to write everything down so that everybody has it. Let's look at some units that are common, and let's look at some units that are common in science. We're going to start with the common to us units. This is called the imperial system of units. We're going to specifically look at length for this example. There's not really much I can say about this as a half Canadian, half American resident. The imperial system is dumb, you guys. I don't know why we use these units. Inches to feet, feet to yards, yards to miles. Who made up these numbers? I don't actually know. I don't know anybody who has 3 feet, for one. So I don't know why that's in a yard. So I'm just... Ugh. Excuse me. So these units are dumb. What we want to instead use in science is what's known as the metric system. The metric system is a very convenient unit system because all of the numbers that are involved are powers of 10. And so what we then do is we associate the prefixes here with these numbers. So milli and 10 to the minus 3 are the same thing. Kilo and 10 to the positive 3, or 1,000, are the same thing. Centi and 10 to the minus 2 are the same thing. That's really convenient for us because if we want to do dimensional analysis and convert from millimeters to meters, all you have to do is memorize these conversions, and that's not difficult to do because there's only like 6 of them. Whereas with the imperial system, you'd have to measure every different number for every different interaction. So there would be an interaction between inches and miles, and feet and miles, and inches and yards, and feet and yards, and all sorts of different things to have to do that. And that's miserable. The metric system cleans that all up for us, so we don't have to worry about it. And you can apply these metric prefixes to anything. whether it's meters or seconds or liters or whatever. In your textbook, there should be a table marked Table 2.2. I have actually printed this on... I printed Table 2.1. Table 2.2 has a bunch of imperial to metric conversions. You don't have to memorize those. In fact, in an online class like this, you don't have to memorize much of anything. You're always going to have this information handy. So don't commit any imperial to metric conversions to memory. Don't tell me how many feet are in a meter. I don't care. Nobody cares. Your trivia night might care. I shouldn't say nobody cares. But you do not need that specifically for this class. If this were in person, I would make you memorize the metric to metric ones, which are coming up in a few pages here. But because we aren't, you'll just need to be familiar with these and have them accessible. So the first thing I want to talk about are what are the types of measurements that you're going to actually make. So what are the dimensions and what are their meanings? So the first one that we're going to talk about is length. Length is the distance between any 2 points in space, which you're probably saying, well, yeah, of course. You could measure your height in length. You could measure the length of a table. You could measure how long it takes you, or not how long it takes, but how long you travel to go to work. I mean, if we were going to work. The unit that we're going to be using is meters. Volume is the three-dimensional space that any object will occupy. There are many units for volume, but the one that we're going to be using is liters. To envision what a liter is, imagine a 2-liter bottle, which we've all bought soda before, I presume, and then just cut it in half, right through the middle. Half of it's 1 liter. The amount of matter something's got is called its mass. We're going to measure mass in grams. You may also see the unit kilogram, commonly used in mass calculations. This is because for physicists and engineers, typically speaking, grams are too tiny for them to manipulate conveniently. In chemistry, grams is actually very convenient because we don't want to make kilograms of chemical waste. So just be mindful that you might see kilograms pop up in some equations in other places, and that is normal. Time is the interval between any 2 events. Time is pretty much exclusively measured in seconds. And then finally, this is a unit that will probably be new to a lot of you. We do have a way to count quantity. So how much of something you have can be measured as a bunch of collections. So I could tell you that I have 12 donuts, for example, or I could say I have a dozen, where a dozen is a collection of 12 donuts. The unit that we use in chemistry is called the mole, where a mole is a large number of things. In fact, I'm going to write that on the screen for you, just in case you're curious about it, because this will come up later. So 1 mole of stuff is equal to this number of stuff. And I realize I should have picked a different word other than stuff. Like, 1 mole of things would be that number. That is a ginormous number. In fact, if I tried to write that number out without using scientific notation, my zeros would fall off the screen. They would end up in the chat box. There would be so many zeros. That would not be convenient for me. Fortunately, scientific notation is a thing. We're going to use it later. Now, all of those units that we just talked about reflect a very specific fixed quantity of the stuff that we're going to be working with. For example, a meter is just like if you spread your arms, not out all of the way, but a little bit, what space your hands will encompass if you're putting your hands in front of you is about a meter. That space is fixed, and we've defined specifically, like, this is a meter. We're not going to do anything else with that specific unit. That's going to be our definition. But if we want to measure things against a meter, and those things are extremely large or small, the meter becomes a little bit inconvenient. For example, measuring the distance to the moon in meters would be a very long journey. We just take our yardstick, we go 1, move it up to the end, 2, move it up to the end, 3. Likewise, trying to measure how thick your hair is on a meter stick is not really helpful. The strand of hair would not even make it to the first mark for a millimeter. So if we want more or less than the quantity that is represented by a base unit, we have to adjust it by using prefixes. Now, the prefixes are going to be shown on the next slide. They are in Table 2.1 of your textbook. And if this were an in-person class, I would make you memorize them. However, you don't actually need to memorize them for this class because, again, they will be provided to you. Having them handy for things like the nursing program here, or maybe later on like the NCLEX, all of those things may have that expectation that, hey, you should know your metric prefixes. So committing those to memory may be to your benefit. Here are the ones on the slide. The red ones are the particularly important ones. I don't need to highlight them because I've already done that. But what these numbers do is that they represent a quantity that is linked to a number. So I'm just going to highlight one. And then what I'm going to do is I'm going to do this. And very conveniently, the one that I highlighted is still in the box. That was not planned. That was serendipity. Let me grab my pen here, because I can't actually see. Let me do this. There we go. Okay. So I should be writing in a color. Okay, I am. All right. So what this means is that if I have something that is mega, so I'm going to use meters for this. So for example, a mega meter. If I have one of those, that is going to equal some number of just the base unit by itself. And that number is shown in the highlighted part of our table. And so the way that this works is that if I have an equality like this is an equal sign in the middle here. Both sides of this equality have to have something of equal value on both sides. So I can't say, like, over here, I couldn't do this, 10 equals 3. Like, that's not true, right? Because that's not an equality. 10 does not equal 3. But this statement up here, in order for it to be true, I have to write it such that I have something of equal value on both sides. And so the way that we do that, let me choose a different color here, is that this right here and this right here are the same thing. And so that's how we interpret the chart. When you are making these relationships, because you're going to have to do this for different relationships on the chart, and then when you're using these terms to do dimensional analysis, you have to have something of equal value on each side. If you don't, and you put the number and the prefix on the same side, then it's not an equality. It's just whatever it is you wrote down. So be very mindful that you put the prefix and the number on opposite sides. So then our equation would look like this. 1 megameter equals 10 to the 6 meters. Let me make my 1 a little bit thicker there. There you go. This would be a true equality. For practice, what I want you to do is write out the relationship for milli, which is just over there. I'm going to do this so that you can see it. I hit the wrong button. Hold on. There you go. We'll make it wider. I'll just do that. And so what I want you to do is, using that relationship at the top, I want you to write an expression that relates millimeters to meters, and use that number to make a relationship. You can try typing out your result in the chat. Typing in exponents is challenging. Use the caret function, which is actually this character, to represent an exponent if you would like. I'll give you a minute or two to come up with what you think is a good relationship following what we just discussed, and we'll go over the answers in just a second. Excuse me. I had to go get some more water. Alright, so it looks like we have some people that came up with the answer. Let's show how we get this result by clicking on the paintbrush. So let me get a new color here. Let's do whatever this is. So at the top there, I have milli and 10 to the minus 3, so I'm going to put my equals down. And so I'm going to put milli on one side. So there's my milli. And then I'm going to put the 10 to the minus 3 on the other side. And then we got to put a number 1 there because I got to have 1 of something. And then I'm going to condense that down to a prefix. So 1 lowercase m for millimeter equals 10 to the minus 3 meters. There you go. You're all set. So you're going to be asked to create metric conversions using this table. And this is the way to do it. Make sure that you remember when you put a number down, you put the prefix down on the other side of the equal. All right. Again, the ones in red are going to be the ones that you want to memorize. Those are going to be the ones that are common. And I'm saying that as if you have to memorize anything in this class. But later on, these will be the ones that you work with the most. Giga, Nano, and Pico are common enough for like hard drives, which would be like gigabytes or RAM or whatever. Nano and Pico are for more like atomic distances, things like that. All right. Now that we've explored some different units that we can measure, let's talk about how you do the actual task of measuring. Believe it or not, you may have been taught how to use a ruler a long time ago, and 95% of us were taught it the wrong way. Or maybe we weren't taught it, we just picked up a ruler and we're like, oh, it's fun to measure things. And then that was all the experience you had. But getting the same result every time, and getting the same result as somebody else who is using the tool, is very important. Particularly in a profession where you are administering quantities of medication to people, if you don't administer the correct amount of medication using the tool correctly, I would invite you to talk to the mother of the daughter who you overdosed. I'm sure that that will end well for you. Therefore, it's definitely in your best interest that you know how to use any tool and know what the marks on it mean and how to get the same result every time. Now, it turns out that when you are making any measurement, it's really, really uncommon to have an exactly correct measurement. There's always going to be some degree of error associated with it. Let's talk about when numbers are exactly whatever their value is. An exact number is any number that has no uncertainty associated with it. If we were all in a room together, I could count the number of people in that room, and I'm just going to use the number of people that are enrolled in this class plus 1 for me. And so if I said that there were 25 people in this room, it would not make sense for me to say this part. This part right here is kind of dumb because you can't have 0.1 of people. People are discrete entities. You can't have a fraction of them. So this doesn't make any sense. We wouldn't include this with this measurement or determination. The next thing that we would determine to be an exact number is just something that I say is an exact number. We're allowed to declare, by definition, numbers that are exact quantities. For example, in the previous slide, we said that a gram and a milligram are related by the factor 10 to the minus 3. So we said this. From the previous slide. If I were to take both of these numbers and divide by this amount, then this relationship would actually change. If you go to your calculator and you type in 1 divided by, and make sure you put the parentheses, 10 to the minus 3, you actually get this as your result. So that relationship right here on the bottom and this relationship on the top are actually the same thing. Now, this one's going to be more useful to you because this is the one you can construct using the numbers on that table. That, again, you're not supposed to memorize, but I'm going to keep saying you should memorize. Just out of habit. However, the 1,000 milligrams to 1 gram conversion is valid, and you can use it if you choose to. Okay? The important part here, though, is that we chose these quantities to be related to each other. We didn't actually go out and measure 1,000 milligrams and then say, okay, that's a gram. We just said, okay, I'm going to make it so that 1,000 of these is one of these. End of story. That's just, we're defining it. These types of measurements are exact quantities, and these are the only exact quantities. So the only way that you can get an exact quantity is to either count or to define. So things that are exact must be one of these two quantities. And if it's anything else, that's the wrong tool there. Oh, boo, hold on. I chose the wrong pen. So that's supposed to be the word anything. Anything else is inexact. Now, what do I mean by inexact? What that means is that if I am... Oops. Well, that's on your slide. We've already talked about that. What I mean by inexact is that if I were to measure this object right here, and I was going to find its measurement in centimeters, the result that you get does not exactly describe its length. For instance, I could not write this measurement down. 11.58239.174348265.9. Like, at what point do I say, okay, this is ridiculous? Like, you're just making up numbers. There's no way you know those numbers with this ruler. Some of these are, like, smaller than the width of an atom going down this far. So the question becomes, which numbers do we get to keep? And which numbers are just garbo? And so in order to do that, we need to devise a way that will reliably give us reproducible results and measurements. Excuse me. And the way that we do this is to use the following rules. I don't have that slide in here. Hold just a second. Let's see here. Oh, I do have this algorithm in here. Okay. So what we're going to do... Sorry, I have two versions of this slide. I didn't know which one I was on. The way that we're going to do this is we're going to look between the two marks that our object falls between. So this green line right here is the length of our object, and these blue arrows represent the scale upon which my object falls. I'm going to use that as a reference in order to tell me what I should measure. The lower mark ends up being 11.6, and the upper mark ends up being 11.7, so I know my object is at least 11.6 something. If I had to guess the next number, I wouldn't pick a number like 0 or 9. So writing down this measurement or this measurement, these don't make sense. Like, there's no way that it is 8/10 of the way through between these two. And it's certainly not at the very beginning of this mark. A more reasonable guess would be something like this. These all seem pretty good. It's about halfway. Maybe it's a little bit less than that. And then, of course, because these are measurements, we also have to include the units, too. So these measurements would be good, but these measurements would be wrong. And the reason for that is because we have some information to determine, hey, this can't be a 0 or a 1 or a 9 or an 8. But it could be a 3 or a 4 or a 5. What you'll notice about this is that the last digit... Oh, I can't use that color because that's the same color. The last digit that we have here is different regardless of what measurement we took. Maybe person A got 0.64, this one got 0.65, and person C got 0.63. I would say that all of those are right, but because of how our eyes work and our eyes aren't the same, my eyes aren't as good as they used to be, for example. So if you're younger, you might be able to tell, oh, that's definitely 0.64. I might just be like, oh, it's about halfway, but I can't tell. They're all correct because we can eliminate some information based on where our object falls again. But there will be some error. Because of that, all measurements will be just like this, and we have to say that all of these measurements would be inexact. We're not going to get exactly the same result at all. Furthermore, do any of these represent the true length of this object? Well, it turns out no, because it's not going to be exactly 11.64000000 off the screen centimeters long. There's going to be other numbers, but we just can't tell what those numbers are without using a better tool. Oops, I gotta clear the text off of the screen there. There we go. So this would be an appropriate measurement to make for this. Let's talk about the rules that you should follow in order to get a reproducible measurement to this degree of precision each time. The first rule is to identify the marks that the object falls between and write down the digits that you know for sure. In this example, I knew that my object would be 11.6 something centimeters. It can't be 11.7 because that would require it to end up over here between these two. Since I know it's 11.6 something, I can write that number down. Then I'm going to guess one more digit past that as best as I can based on what I see. Because this looks like it falls a little bit before the midpoint, I guessed 11.64 as my measurement. So what this means is that the marks are going to govern how your measurement is written down. You're going to write down the value based on the marks, and then you're going to guess one more digit than the marks tell you, because your object will fall between those marks, and you can guess that number. But you can't guess any more than that. Let's look at a few more examples here. What I want you to do is use ruler A and ruler B and determine the length of this wooden dowel. Type your answers in the chat when you get them, and don't forget to put units on your answer. And I want you to express your answer to the correct number of positions that you know for sure. So like maybe 1 decimal place, 2 decimal places, maybe no decimal places, 20 decimal places. Write out your answers, and we'll go over the answer in just a second. All right, that should be good enough for time. So I see a bunch of answers. Let's talk about what you need to do to get those answers, and we'll check to see if they're right. So here's my mark. It's going to fall right here. So my object is going to fall between these two marks. So I'm going to write down the number I know for sure. It's 4 point something. And then I need to guess the next digit. So I'm going to guess not 0 or 1 or 2 or 8 or 9. I'm thinking it's right in the middle. So I'm going to guess 5. And then I'm going to write the units. There you go. That's the first one. For the second one, here's my object right here. Oops. It falls between these two lines, 4.5 and 4.6. So this is 4.5, that one's 4.6. So now I have 4.5 something. I'm going to guess the next digit to be probably 5. Could be a 6, could be a 4. Somewhere in the middle there. And there you go. I realize the answers are on your slides, so don't peek at the slides unless you want to know the answer. Now, remember again that the ruler will dictate, with its marking, how many digits you get to write down. So you always get to write down what the marks tell you, and then you get to guess one more. Now, based on the numbers that you write down, that's going to tell you something about the instrument that was used. For example, let's suppose that I gave you this number, and you didn't know anything about the ruler. What could you conclude about this? Well, if you remember that the numbers that you know you write down for sure, and then the last one is the one you guess, then that means that the tool that's used would measure to every 0.1 centimeters. And so you could then guess to the 0.01. Knowing how much precision you have available is important in comparing two numbers together. We're going to summarize this sort of thought process as a way of just counting the number of digits we write down. And the reason that we're going to do that is because... Oh, that's not what I meant to do. Erase all. There we go, that's what I want. The reason that we want to do that is because this is a much shorter method that gets us a reliable result. If I write down 4 digits and I know them all for sure, what I would do is I would say that this value has 4 significant figures. Or in other words, 4 sig figs, which I'm going to abbreviate as SF. A significant figure is any number that you know for sure or you have closely estimated. It is not a number that is guessed at random, so we can't count just randomly written down digits as significant. They would be just random. So this value here has 4 sig figs. If I had a larger number of sig figs, like this, which has 9, this number would represent something that was measured with a much more precise tool. To get this distance, I would need to have something that had like a laser guide and was calibrated frequently and was probably powered by magnets or something ridiculous. I don't know. Now again, you can figure out what the tool is by looking at the number that is being measured. For instance, here are 3 graduated cylinders, but only one of these will allow me to measure a value of 540. What are the values of the quantity of water that you should write down for each of these 3 graduated cylinders, noting that graduated cylinder C is just zoomed in really close? So what I want you to do is try and estimate these 3 measurements and pick which cylinder would be the one that gives you 540. So I'll give you 2 minutes to do that, and we'll go over the answers in a second. All right. So it looks like I see some answers popping up on the screen. Let's write down these numbers and see which one actually becomes 540. Could everyone be wrong? It's unlikely, right? All right. So here are my marks on this one. There's actually a mark at the bottom that's invisible, but it's also known. If you had absolutely nothing in the jar, it'd be 0. This first mark is at every 1,000. I actually don't know what this mark is right here. I'm not sure why that's there. We're going to ignore it. This device measures every 1,000, so I would write down the first digit, which would be 0,000. This falls about halfway between, so I would say that there are 0.5 thousand, which in normal numbers would be 500. And that would be the result that I get for this graduate cylinder. We're going to assume that these are in milliliters because the target one isn't. No, the answer, it's shown. I touched the pen again, I'm sorry. Where'd my cursor go? There it is, okay. For this one right here, my liquid falls between 500 and 600. I know that I have at least 500, so I'm going to guess that to be 4/10 of the way through, so we'll call that 540. I was about to write 550, and then I realized, oh, duh. That's the answer. And then finally for C, these are my marks, so I know I have at least 540 something. I'm going to just call it 544. So B is right. Everyone's right. Hooray. Now, because there are more marks on graduated cylinder C, we get the most sig figs. Because there are the fewest marks on graduated cylinder A, we get the least sig figs. So that's the relationship between sig figs and the number of marks on your device. The more precise it is, the more digits you get to keep. All right. When I look at a number, it's really important to realize that sometimes the digits you write down have a purpose that is not necessarily identifying how much value there is there. And what I mean by that is, specifically, the number 0. If I write this number down, then I know that I have a quantity between 3 and 5, we'll say. But if I write this number down, putting a 0 there doesn't add no value to it. In fact, it changes its value by a factor of 10. And if I put a bunch of zeros in place here, these zeros are important, but not because of their value. It's because of what they're doing. They are adjusting the magnitude of my number. For example, let's suppose that I owed you some money. I'm going to say that I owed you this much money. And because I'm nice, I'm going to round it up to this value. And then what I'm going to do is I'm going to say, well, 0 has no value, so I don't need to write it down. And this is the amount that I'm going to pay you. Would you be satisfied with this transaction? You can type your answer to this question in the chat, and very obviously you're going to say hell no, because who would exchange $3,992 for 4? That's kind of silly. When I have a number... Yeah, you didn't actually have to do that one. That's okay. Immediately everyone was like, no! No, I want my money. Of course you do. These numbers have some meaning. And if I do rounding, I need to retain that meaning in the rounding. So what I need to do is I actually need these zeros here as what are known as placeholders. They adjust the magnitude of the number so that the magnitude of the sig fig that I have makes sense. So if I have a number that is non-zero, it will always be a sig fig. But if I have a 0 in there, if the 0 is a placeholder, it's not a sig fig. It's just using the property of placeholders and how numbers work to put that 4 in the correct position. In the tens place, in the hundreds place, in the millions place, whatever. Let's look at some examples of when 0 is a sig fig and when it's not. Here are some numbers. That's the example I just went over at the top. Here are some numbers where the zeros have a specific meaning, but they don't actually affect the value. For instance, and let me get my highlighter out here in a really dark color. If I were to... That's not the right color. Hold on. There we go. If I were to cover up the... I still didn't. There we go. If I were to cover up these numbers, does the value of the number change? Ignoring the fact that I covered up this 5 here. And obviously it does, because the number that we previously had is very different than 125. If covering up the zeros changes the value, those zeros are placeholders, and thus they're not significant. The same thing happens down here. If I erase these zeros, now I have a number that's 4,000 or something. But if I keep them, now I have a number that's incredibly tiny. Therefore, these zeros were placeholders. They were used to put this in the correct magnitude column so that we have a value that matches whatever it is we're measuring. So if I took this measurement for something tiny, it would make sense. Whereas if I said something was 4,000 of a unit for a tiny object, that might not make sense based on what the unit is. And again, covering the zeros with your hand is a good way to tell if something is a placeholder or if it's not. And so that's what this is. Now, there are some instances where 0 can be a sig fig, and that's based upon what we specifically do that leads us to get to 0. For instance, let's suppose that I have this number here. If I were to cover up these zeros and get rid of them, then the number that I would have would be much smaller. So these zeros must be placeholders, and therefore they're not significant. But this 0 in the middle here, right here, should we count it? And it turns out that the answer is, yes, we should count it. And the reason for that is because of the following. If I have a scale like this, it's not a very straight line, but that's okay. And the boundaries of my scale had markings that represented the second to last position, because remember, all of these numbers would be known for this measurement, and then this one right here would be my estimated, the 9. What that means is that this mark would be 8, 6, 7, 5, 3, 0, 0, 0, 0, 0, 0. And this one would be 8, 6, 7, 5, 3, 1, 0, 0, 0, 0, 0, 0. Now that I've said that out loud, did everybody get the joke? In order to land on this as my estimated digit, what my object would have to do is be something like this. And if I have that as my object, then I would say that these are the numbers that I know for sure. One of them ends up being this 0 here. And then I would guess the next digit to be 9. And then I'd put the rest of those zeros that are insignificant there. So, in other words, these marks are measuring to this... Oops, sorry, hold on. I moved my pen and then started drawing under the wrong number. We're measuring to this position, but it just so happened that our scale had a 0 in there. Now, obviously, this is a really big number to wrap our heads around, so I'm going to do a different scale over here. And so if I were to measure to the ones place for all of these, then I would get a number that would be good to the ones place, but then suddenly for this one, I would only be good to the tens place. So this would give you 3 sig figs when you estimated your number. But this one, for some reason, would only give you 2? That doesn't make any sense that this part of our scale, when everything is all the same, should be any different. So if I measure something around this area, I should still be able to write 40.1 or 40.0 or whatever. Oops. So whenever you have a 0 that is stuck between two numbers, if those numbers are sig figs, the trapped 0 is a sig fig also. Okay. So any numbers that are sandwiched in there will always be counted. The last rule that we have for sig figs and zeros is the decimal rule. The decimal rule is a special rule that you must follow if you have a 0 and a decimal point present. Okay. So here is our decimal point. Here are some zeros that are present. We're going to need to consider the decimal point rule. Here's how we do this. So step 1, find the decimal point. I already did that. It's right there. That means we must use the decimal rule. Step 2, underline anything that isn't a 0. That's these guys. So I'm going to count those sig figs for sure in my sig fig determination. Finally, for step 3, anything to the right of what you underlined is a significant figure. Anything to the left is a placeholder. Those are just zeros that are moving your magnitude to where it needs to be. But the other zeros on the right side are known, and I'm going to draw the chart for that in just a second. So these zeros are significant. These zeros on the left are placeholders. And so if I asked you how many sig figs were in this measurement or calculation, you would say that there were 7 significant figures. I need to set something up really quickly on the previous screen here. And it's not actually working for me for some reason. I could do this. Sorry, I'm trying to get my... There we go, that's what I want. So when I do this... There we go. So if I was going to make a mark for this number on a sort of scale here, then what that would look like is this. So here is my mark. Oh, I'm zoomed in really far, so this is going to look really weird. Hold on. So I'm trying to get rid of those dashed lines. I don't know why that appears on here. So if this is my guide... Oh, why is this happening here? That works. Okay. If this is my guide here, and the number that I'm working with to get that measurement was something like this. Actually, let me put another mark in the middle here. 0.003835. Actually, that's not going to be the right number, so let's do... I didn't set my layers again, that's okay. I want to just make sure I get the right number of digits here. There we go. So let's suppose that we have these marks for our tool here, and our object was to fall right here, right on that line. Since I am measuring to this position for all of my numbers, I would write down that I know those numbers for sure, and then when I try to guess the next digit that should go next to it, since it landed on the line, I could end up guessing 0. So if you have really small numbers and you just happen to land on the line, the possibility that you have a bunch of zeros is very real. And so you might have a measurement that requires you to keep a bunch of zeros. And those zeros can still be significant because in our measurement here, all of these numbers were known because they were known off the scale. This last digit was estimated, and it happened to just be right on 0. So we could keep that one too. All right, let me minimize this, get this out of the way. All right. On the board, I have some more examples here. Going through these examples, get my pen back out here. These 3 digits are non-zero, so they are significant. But these 3 zeros are placeholders and thus are not, because if I were to remove them, now I have the number 123. Therefore, since that changes my value, this must be a placeholder. These 3 zeros are also placeholders because they change my value to the thousands. These 4 digits are not 0, so they are significant. So I'd have 4 sig figs for this one. Here I have 3 ones. They're all significant. These zeros are stuck in the middle. They are significant too. The other zeros are placeholders. And then finally down here I have the decimal rule. In a decimal, everything to the right of a sig fig is also a sig fig. Okay? So what I want you to do is I've given you a series of numbers. Using those numbers, what I want you to do is tell me the number of significant figures in the measurements, okay? And then there's the homework practice on the board. I realize that chapter 2 might also be incorrect. I have started to go through these and edit the ones that are wrong. I'm going to upload them all at once, probably tomorrow once I have all of it done. But for now, determine the number of significant figures in each measurement. And what I want you to do is count them and then underline them on your paper, because that's what we're going to be doing here. I'll give you 2 minutes to do that. Then we're going to take a break once we go over the answers. So go ahead and get started. All right, let's go over the answers. And I actually want to put this on the screen here. So I'm going to read this in a second. An email from the college president. Some information that might be useful to you guys. All right, so the number 900 right here. We're going to underline this digit because it is non-zero, so it's significant. These zeros are placeholders. There is no decimal point. Therefore, there is only one significant figure in this value. This sentence apparently is this part of this sentence is no longer true, which scares me. And I also heard they canceled it immediately, so that's also good. But anyway, 90210 is an old show. I wrote this slide years ago, and it was still old, and then suddenly they revived it, and maybe it was my fault? Anyway, these are numbers that are not 0, and therefore are significant. This 0 in the middle is trapped. This 0 on the end is a placeholder, and is not significant. For the third answer, we do have the decimal rule involved, so these 8 and 7 digits are significant. Anything to the right is also significant, so I must have 3 sig figs there. Now the last one, you'll notice that I wrote 500 and I put the decimal at the end here. There's a specific reason that I did that, and the reason for that is because this forces you to use the decimal rule, which means that if I have this 5 here, everything to the right of it is also significant, and therefore gets counted. Now you might ask yourself, well, that's rude. Why would I ever care about doing that? Well, if you had an answer that you wanted to ensure had 3 sig figs, if I were just to write 500, as written, this is only one significant figure. But doing this with this stupid dot that's hidden there ensures that I get the correct amount of precision for this value. Now here's a challenge question. How would I write 500 with 2 significant figures? Is there a way to do it? And the answer is, there is a way to do it, but not with this notation. What I actually have to do is do this. Because then, now I have the decimal rule. This is a sig fig. This is to the right of it, so it's a sig fig. And I have only 2 digits there. And then 5.0 times 10 to the 2 is 500. So it has the same value, but it has the correct number of sig figs. In some instances, you will need to use scientific notation to both report your answer or just to do the calculation. We're going to go over scientific notation a little bit later on. But for now, we're not going to go over anything because we're going to take a break. So let me put the... Well, first let's go to the next slide here. We'll save the math for when we get back here. I'm going to go to the title card. I'm going to turn on the timer. Boop. I'm going to turn on the break time announcement. Boop. I'm going to hit the timer, boop, and I'll see you in 10 minutes. Oops. I kind of sat there listening to the music because this is one of my favorite songs on the soundtrack. I'm like, oh yeah, we stop the break at like 10 minutes, so let's hide these. Boop, boop, boop. All right, hopefully everybody is back from their short break. Chemistry is hard, but like anything in life, it's hard until you do it once or twice or 86 times. So the best recommendation I have for you is to practice, 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 practice. If you don't use it, it goes away. Like I haven't really done anything in like English for years. Like I remember in high school I had to study like tone and stuff like that. And now I don't remember much of it at all. But the math part of it I've been using pretty much every day since high school. So I remember all of my like algebra and calculus and stuff. And it's just because I keep doing it. Anybody can be proficient in chemistry. You just got to work a lot of hours, really. So don't give up. We're going to do some mathematics today. We're going to do simple math. And we're going to use the rules that we just talked about for sig figs and apply it to mathematics. Now, what's important is that the rules for significant figures aren't just a curiosity. They don't just go away because we don't want to use them. They're here to stay so that we can get calculations to the same degree of precision that everybody else does, so that you would eventually administer the correct amount of medicine to my cat, basically. This is where we're going here. There is a slide later on, which is like, here's my cat. Please don't overdose my cat. And if you don't have the right number of sig figs, then you don't give her the right amount of medication, and then I am a very angry customer. And yeah, please don't kill my cat. That's basically it. We got to get there, though, so let's start working with some other operations that are very common calculations that I'm sure that you've done many times in elementary and secondary school. On the left, I have an addition problem. I'm sure everyone can do that. On the right, I have what is the area of this rectangle problem, which requires you to just times the numbers together. Everyone can do that too. However, I'm sure that we have all grown very reliant on our calculator because it's always handy, and at some point we just make the assumption that, hey, I know how to do math. I don't need to do my addition vertically anymore. I don't need to multiply using that vertical method where you start putting little X's and then you move everything over a column and then you add it all up at the end. I don't have to do those things anymore. You might have told yourself. Well, today we're going to come back to those because remember, all of the mathematical operations that you do in this class are going to require you to use significant figures. So let's consider those implications when we do these problems. On the board here, I have a problem where in the past, and I don't want this color because it's not bright enough, or dark enough, I should say. There we go, okay. In the past, if I was going to add these numbers together, you'd look at these blank spaces and you'd say, well, these are just 0. Anything that's blank, we're just going to treat it as 0, and so I'm going to just add vertically. We'll carry the 1. 11, 14, 15. Man, I had to carry all these 1s, didn't I? There we go. And you would report this as your answer. And in first grade, or whenever you learned this, that would be correct. You just add all the numbers up and just go straight down, and everything is great. But in reality, if all of these terms are measurements... I lost my cursor again. If all of these terms are measurements, then we have an issue. And that issue is this number in this space right here is not 0. In fact, it's a question mark. So is this number in this space right here, and this one too. And now if we try and do the addition, and I say, what's 1 plus question mark plus question mark, is the answer 1? And you should immediately go, I don't think it could be 1. It could be any number, really. So this becomes unknown as well. The same is true for this number right here. In fact, we lose these digits because of these question marks. Because if these are measurements and those numbers aren't written down, they're not significant figures. They could be any number. We don't know them. So when we do addition, with significant figures, we have to consider this possibility and only report the numbers that we know for sure. Everything else gets rounded away. We don't get to keep it. So the way that we're going to do this in this class is to follow the following algorithm. And here's how this works. The first thing that you're going to do is you're going to start from the right side, so over here somewhere, and you're going to consider which position contains significant figures for all of the values you're looking at in the problem. So I'm going to start over here in the thousandths place. Is there a significant figure in every value that we are adding together? And the answer is, well, no, because there's not a significant figure here or here, so I can't use this place. How about in the hundredths place? Can I use the hundredths place? Nope, I don't have a number up here. I can't do it. How about the tenths place? Number, number, number. Oh, there's a sig fig in all three positions, so I can round my result to this place when I'm done. Once I have determined the position that I want to round my results to, then all I have to do is actually do the math. And so I would do that like normal. That's the number I got on the previous slide. But I'm going to round to this position that I circled previously. Okay? That eliminates any error from those question mark numbers because we aren't going to have them in our answer. All right, let's do some examples, and we'll do this process a few times. What is this calculation? So what I'm going to do is first I need to find it wherever it is in my thing there. There it is. And then this should disappear because I erased that already. All right, let me get my pen. That is not a color. All right, so we're going to write this problem vertically. And whether it's addition or subtraction, it works out the same way. You just set it up vertically and solve. All right, there's our numbers. Which position will I work with to report my answer? So let's start from the right. We're going to go to the first position here, which is the hundredths place. Can I use the hundredths place? Nope, there's nothing there. I can't use it. Let's go to the tenths place. Yeah, this is the tenths place. Can I use the tenths place? Yeah, I can. So I'm going to report my answer to the tenths place when I round. So 4.83 minus 0.7. 3 minus a blank is 3. 8 minus a 7 is 1. 4 minus 0 is 4. Let's put my dot in there. And again, I'm going to go to the tenths place. So the answer that I would report would be 4.1. All right, so hopefully everybody was able to follow through with me to get that same answer. Let's do another one. This one will be a little more complicated. What is this calculation? How the heck do I do this? Well, let's find out. So I'm going to add these numbers together. 7,300, 139.228. We're going to add. There we go. All right, first things first, we need to figure out which position we can add to. So remember, we need a significant figure in every position, in the same position in all of the values we're adding. So we'll start with the thousandths place. Obviously, that's not going to work. Hundredths place, no. Tenths place, no. Let's go to the ones place. Is there a significant figure in both of these numbers? And the answer is No. This is a placeholder, so I don't get to use that place either. How about the tens place? This is a placeholder. Can't use it. How about the hundreds place? The hundreds place works. I am allowed to use this number. So I would round my answer for this addition to the hundreds place, which means that when I do this addition, if I'm rounding to the hundreds place, the number that I would report is not 74, because that would change the magnitude of my answer. 74 is not a number that has a value in the thousands, so I got to add those zeros back in for placeholders. So there's my answer, 7,400. All right, here's the last problem. If your brain isn't broken yet, this one will do the job. Oh, I messed up on my thing. Hold on. There we go. Oh, Photoshop, why are you being a pain? There we go. Okay. So we're going to do 3,000 plus 6, using the rules that we've just established here. So again, we need to work from the right, choosing the first position where there's a sig fig in each of the values. Is there a sig fig in the ones? Nope, because this is a placeholder. How about this one right here? Nope. Hundreds place? Nope. Thousands place? Now, technically speaking, there are zeros in all of these places in front of the 6. We just don't write them. But what's important is that they are known. And so if I get over here and I say, is there a sig fig over here? A sig fig being a known number, I could say, yes, this 0 is known to be 0. And this 3. So I would round to the thousands place. Which means that in this class, 3,000 plus 6 is 3,000. And that's the sound of 24 brains exploding. You might be looking at that and thinking to yourself, what the hell? Who the heck decided that this was the answer? In fact, I even accommodated for that in this slide. But it turns out that this sort of calculation, as unintuitive as it seems for this example, actually makes a little bit of sense if we consider some real-world problems. For example, let's suppose that you decide that chemistry is too hard and you just don't want to do this anymore. You're going to find a new path through life. You're going to play the lottery. And it turns out that you win. And it's a pretty good pot. You win. I don't know why. Oh, I have an eraser here. I didn't even realize that. That's nice. Anyway, you play the lottery. And you win this much money. $656 million. But you're new to this millionaire thing. So you go out and you spend some money on dinner by buying a Big Mac for $8. How much money do you have left? Does it make sense for you to do this? Would this be the amount that you would report to all your friends, how much money you have left? Or would you say, I don't give a shit about these numbers anymore. They're beneath me. And just report this as your answer. Because the hundreds place, the thousands place, you could throw around $10,000 and it wouldn't even affect your bottom line. $10,000 to you when you've won this much money is called walking around money. You could just throw that to random people on the street and change their lives, and that information, or not that information, that would not change the magnitude of the money that you have. You could be Jeff Bezos. Hint, hint, if Jeff Bezos is watching this, start giving people random money. It won't affect you, because sig figs. That's why sig figs are important, right? The fact of the matter is that these two numbers are very different in magnitude. And when numbers are too different in magnitude, and you try and combine them using addition or subtraction, you don't really affect the larger of the two numbers. Another example would be if we were calculating the population of Seattle, and it was something like this. And then I said, well, this weekend a family of 4 moved in. How many people live in Seattle? Well, I would still report this as the number of people that live in Seattle, because that 4 is not going to affect the estimated number of people in Seattle. There certainly are not exactly 700,000 people in Seattle, and it's impossible really to know exactly how many people there are in Seattle, because people come and leave all the time. So, considering the rules for significant figures, it's very important to understand that if you have numbers that are really far apart and you try and work with them, you do get weird results. And that's part of just how addition works. And that is intended. All right, that's addition. Let's move on to multiplication and division, which are the same process but have different rules. So what I want you to do is I want you to note somewhere on your slide that these are different rules. Okay? The reason I want you to do that is because everybody learns the addition rules, and then they learn the multiplication division rules, and then at some point students say, oh, I like this rule better than the other for whatever reason, and then they apply that rule to everything. You can't do that, okay? That would just be like, I like sugar, so I'm going to put sugar on everything, including my pizza and my steak. Like that, you can't do that. It doesn't work, right? Same thing that happens here. You can't do the multiplication rules using the addition rules. You get the wrong answer, okay? So just be mindful of that. For what it's worth, multiplication and division sig figs is a lot easier. I'm going to find the area of this rectangle. To do that, I would multiply these numbers together. However, if I were to line these up in the same way that I did the addition before for multiplication, and the reason that I'm doing this is just to have them to the same degree of precision, what I would end up doing is I would end up having a lot of Garbo numbers when I do multiplication, and then I have this x because I have to carry over my place when I start multiplying in this position. And so these would all be question marks. Doing this, I would have a bunch of question marks here. It would only be when I got to the 4th digit that I would actually start writing down numbers. And then you know how you do that addition at the end? Everything over here on this side is all question marks and is Garbo. Only these numbers would be useful. I'm not going to actually do the long multiplication for you because that would just take way too long. But if you remember something about long multiplication, you probably can follow along with what I'm doing there. If not, it's no big deal. We're just going to fast track straight to how to do the problem. And the answer to this problem is, well, I'm going to punch it in my calculator, but how is this answer going to affect my result up here? The first thing we're going to do is we're going to look at how good our values are. How many sig figs are in each of these numbers? So in 14.2985, there aren't any zeros, so we would say that this number has 6 sig figs in it. In 6.4, none of those are zeros, but there are only 2 digits there. Then finally, what we're going to do is we're going to do the multiplication and write out the number that we get off of our calculator. So grab your calculator, punch in these numbers, times them together, and when you are done, you should get this on your calculator. 91.5104. All right, so that's step 1. Count the sig figs in each answer. Step 2, write out the answer as the calculator gives it to you. And then step 3 is going to be, of the number of sig figs that you highlighted, which of them is the smaller number? So, which is smaller, 2 or 6? I'm sure everybody is saying 2 right about now. So since 2 is the smaller number, our answer is only allowed to have 2 sig figs, which means that I'm going to keep these 2 sig figs right here and round my answer appropriately. So when you're doing multiplication or division, all you do is punch it in the calculator and then keep the number of sig figs that matches with whatever value has the fewest. If you have 5 numbers and you're multiplying them all together, you just find which of them has the fewest number of sig figs, and your answer will have that many sig figs too. Let me clear all my ink because it's going to reappear on my slide here. Anyway, that's the gist of multiplication and division. Let's do some more examples. We got to go back over here to do that. Oh, I got a little bit of setup to do. Hold on. So, woo, it's moving on your screen. Photoshop, select all, goodbye. All right, I should be able to draw now. Okay, great. Hold on, let me get rid of this thing. All right, so I'm going to do this multiplication. And I did all that without realizing I don't actually need to write any of this down because we're just going to punch everything into the calculator anyway. Go ahead and type this in your calculator, 5.4336 times 1.2. And when you get a number out from that, it should be this. And now we need to consider sig figs. How many sig figs should my answer have? Well, this number has 5. This number has 2, which is smaller, 5 or 2. Our answer should have that many sig figs. And so I report it as such. Let's do another one. Again, go ahead and punch that into your calculator. I want you to tell me the answer when you have done that. And then I will work it out on the board. So go ahead and do this problem. Write down your answer, report it in the chat. Try not to look at my slide on the printout that I sent you, or the PDF that I sent you, or whatever it is. Now make sure you are interpreting that slash there as a divided by. I have a feeling some people are multiplying. All right, see a lot of good answers? Let's go over the answer together. When I punch this into my calculator, it makes a smiley face. No, it doesn't, actually. It makes 91.67368421. That is a lot of digits. 673688421. I certainly don't get to keep that many, so I need to consider sig figs. How many are there in this number? There are 5. How many are in this number? Well, I have a decimal. These two count. Anything to the right counts. So I have 3. What's smaller, 5 or 3? The answer is 3, so I'm going to keep the first 3 that I've got and round appropriately. And you're all set. There you go, good job. Here's the last one. Go go ahead and give this a try. That is a number at the end that has one significant figure. Yes, that's obnoxious, I realize. And you will get a very crude answer as a result. Not crude as in inappropriate, but crude as in, like, no accuracy at all. And this will be a number where you'll punch that and you'll be like, really? The answer is whatever? Ugh. That's intended. Type your answer in the chat when you get it. See a lot of 4s in there. Is 4 really the answer? Well, let's find out. 7.63829 divided by 2 gives me 3.819145. It turns out it's really hard to write when your eyes are looking at a calculator. The tablet has nothing on it, and the printout is on the screen. So that's why I'm, like, drifting up here as I'm writing. Anyway, this has 6 sig figs. This only has 1 sig fig. My answer only gets to be 1 sig fig. And, of course, the answer is 4. As upset as that makes us when doing math, when you're dividing by something with very little precision, it greatly reduces the accuracy of your answer. All right, there is one last thing to do on our calculations lecture, and that is to figure out what do we do if we have both of these operations. I forgot about this slide, actually. Let's do this example real quick. I want you to type this into your calculator, and I want you to type in the chat what your calculator told you the answer was. While you do that, I am going to set up the problem vertically and solve it myself. So go ahead and type in what your calculator gave you as a result. And once you've done that, look at the screen and tell me what happened with your calculator. I mean, you can tell me it out loud, and then I will just not hear you because sound doesn't work like that. But that's interesting, though. Everybody got 8, but I got 8.000 doing it by hand. It turns out your calculator doesn't know what a sig fig is. Your calculator sees those zeros at the end, and it sort of just chops them off. Your calculator, well, most calculators, you might have an advanced calculator that actually keeps the sig figs because it knows. But most calculators don't do that. Make sure that when you're doing these calculations in this class, and in any other math or science class that you take at EVCC or in the nursing profession, that you aren't relying on your calculator to just keep all the digits for you. What you need to do is make sure that you are following the rules, and at each step of the way, consider what the sig figs are, make sure you're recording the correct number of digits, and then you won't go wrong. Alright, now the final thing. What happens if you have to do both things at once? What do you do when you have addition and subtraction, or multiplication and division, mixed together with each other? And the answer is, how do I go about doing this problem normally? If you were going to figure this out without even worrying about sig figs, you would follow a very specific algorithm. What is that algorithm? And I assure you that it has a funny little saying that you remember from 4th or 5th grade. You might be typing it in the chat right now. Yeah, that thing, right? So we all remember PEMDAS, right? which stands for please excuse my dumb ass sibling. That's what it means, right? I'm sure that can't be wrong. P is parentheses, E is exponents, M is multiply, D is divide, these go together. A is addition and S is subtraction. Those go together. But we have to do these operations in this order. If you don't do it in this order, you just get the wrong answer. And the reason that this is the order that you have to do stuff in is because, well, we said so. Not we as in me or somebody important. We as a civilization. Like when we devised the rules for math, we said, okay, we have to do it this way because there's infinite ways that we could solve a problem. Let's just pick this one and this will be the rule. So now we can just follow PEMDAS and do all the operations based on this order, but each time we change operations, we'll have to look at sig figs, and that'll affect our answer. So here's how this works. Using PEMDAS, we would say that this part in the parentheses is the first thing that we would do, which is a subtraction. So I'm going to do the subtraction over here. 73.8 minus 70.983. When I do the subtraction, I would find that I can't go to the thousandths place, that's no good. Can't go to the hundredths place, that's no good. Tenths place works, though. So I will do my subtraction. 1, 8, 2. So I got 2.817 from that subtraction, but I only get to keep to this position, which means that I can only keep 2.8 as my answer. Now that I have done the subtraction part, the division part remains. So now I'm going to apply the division rules. And the division rules say, I'm going to punch this number into my calculator, and then I'm going to keep the one with the fewer sig figs. So this has 2 sig figs, and this one has 4 sig figs. So my answer should have 2 sig figs. So we'll punch it in the calculator. 2.8 divided by 2.639. Hit enter. And I get 1.0, a bunch of numbers, which rounds to 2 sig figs, 1.1. So for today's exercises, we reviewed a method that will produce reliable, consistent results in doing addition, subtraction, and multiplication and division. And now finally, everything combined together. Your task is going to be to decipher various algebra problems, just simple math, so stuff like this, and find your way to the correct answer, but report that answer to the correct number of sig figs. That's the critical part, okay? Because anybody can do these problems. You just have a calculator. You just type it in, right? But how do you know whether you report 0.04041648, or do I round somewhere, or what? That's where the rules for sig figs come in. If you follow those rules, everybody will get the same answer every time. So what I want you to do, I'm going to give you 7 or 8 minutes to do this. Around right before we get to 7 p.m., I'm going to put the answers on the screen for you to see. When you have seen those answers, so we talked about it, we'll call it a night. So go ahead and get started while I create a copy of this picture, and I will put all the answers down in just a second. All right, we got about 2 minutes left in the lecture. Hopefully most people have completed at least the first 4 or 5. What I'm going to do is I'm going to push the magic button. And only 4 of the answers are going to appear. So hold on, I gotta fix that. That sort of worked. Okay. There you go. So those are the answers to these problems. That top one that's kind of tiny and faint because I had it zoomed in and my pen pressure wasn't being detected. That's 0.041. For this first problem here, I gotta find my cursor again. For this first problem here, there are only 2 sig figs in this number. There are 4 here, so my answer should have 2. Here I have 4 and 2, so my answer should also have 2. In addition, the first place that I'm allowed to round to ends up being the thousands place. This subtraction went to the ones place. This multiplication here had 4 sig figs for each value, so my answer also has to have 4. That's why I can't do 12.00 with the third 0 there. Here we do the addition first, rounding to the tenths place. That gives us a number that's 40-something point something. I forget what the number exactly was, but that has 3 sig figs times a number with 3 sig figs gives you a number 3 sig figs. For the last one here, when I do this division, my result is like 14.56 whatever, but I can only keep 2 sig figs when I do that division, so my answer ends up being 15. 15 subtracted from 11 can be rounded to the ones place, which I report as just 4. All right. These aren't easy. So if you are doing these problems and you're like, wow, I barely made it through that, I can't believe I got the right answer, then what that means is that you got to do the homework practice. So down here are a bunch of exercises that are more of these types of problems that I want you to do. The level of proficiency that you should get to should be that you do these problems and you get an answer and then you don't feel like, I don't know if I did that right. And the only way to make that go away is to do as many examples as you can. So make sure you're doing every homework problem you can. If you do one and you aren't sure if the answer is correct because either the back of the book has a different answer or it's one of the odd-numbered ones, you can always send me an email. Please don't ask me for every answer because I do want you to develop that confidence. On the exam, I can't tell you if you did it right or not until you have submitted your exam. So you have to develop that ability to get to the point where you're like, oh, okay, yeah, I did the problems. I know I did the rules correctly. This must be the right answer. Let's go to the next problem. Okay? That's going to conclude today's lecture. We're going to return on Tuesday with some more of Chapter 2. We're going to do dimensional analysis. It's probably one of the harder things we do in this class because it involves unit cancellation and all of this stuff that we just did, because this is all going to start building on itself. So make sure you have read the chapter, you've done a little bit of preliminary work and notes. If you have any questions for me for today's lecture, please feel free to type them in the chat. I will leave the stream up and running for a few more minutes to answer any questions. Once I hit close, it does shut down the chat. At that point, you have to send me an email. Good night, everybody. Thanks for watching. Have a good weekend. There is nothing due this weekend. I will have some assignments that will pop up. Don't worry about them until we talk about them on Tuesday. Have a good one, and see you later.